In this video, we're going to just do a couple of optimization problems. Optimization, probably the hardest part, is the beginning, the setup. The calculus is actually pretty easy. We have a rancher with 400 feet of fencing. He wants to build a corral that's divided into 3 equal rectangles. What is the length and width that will maximize the area? Now, I've included here kind of my 6 steps. You certainly don't need to use this. It just can kind of be a nice way to formulate your thoughts as you work. The first thing I always do is draw a picture. So let me do that. We have this thing. It's going to be divided into 3 rectangles. So we're going to put in this. I'm going to label it, just with variables. So x. So I have another x here, and another x here, and another x here. And I can make the top and bottom y. Okay. Next, I'm going to express the thing I want maximized as a function of the variables. Well, I'm trying to maximize the area. Oddly enough, this is always a hard step for people because we play with a couple of different equations in optimization. We need to make sure we know what is the equation of interest, what's the thing I'm actually trying to solve. And that is area here. So area is equal to, in our case, x multiplied by y. Okay? I'm going to leave it at that point. Now, the next step, number 3, says use the information to relate the variables to one another. So now we've got to use what else we were given. Okay? We were given 400 feet of fencing. Okay, we were told that. So that's how much fencing we have. So if we were to add up all of the fencing we used, we should get 400. Okay, so 4 x's and 2 y's should be equal to 400. Now, I'm always looking to make this simple. Okay, so I'm going to divide everything by 2. That. And then, again, you could solve for either variable, but I think it would be easiest in our case to just subtract 2x and have this. Now, the 4th step says, okay, now go back to your equation and put it in terms of one variable. So area was x times y. Now it's x multiplied by 200 minus 2x. And in the interest of, I know there's a calculus step at the end. It would be easiest to multiply in and have 200x minus 2x squared, like that. Next, find the domain, or at least be aware of it. I say this because sometimes, when we're trying to find a maximum, endpoints could possibly be the maximum. Under candidate tests, that idea that an absolute max can occur at a critical point or an endpoint. Well, in our case, in this kind of real-life problem with fencing, we've got our x, that's our variable. It's got to be greater than 0. We can't have a fence length of 0. And if you look at, this red box that kind of defines what y is, if I made x over 100 or even 100, I wouldn't have anything left for y. So my x also has to be less than 100. And I say this thing about domain because really here we don't have endpoints. We're not defined at the endpoints. You can't have x be 0. You can't have x be 100. X has to be greater than 0 and less than 100. So you really aren't worried about endpoints here, but it's a good thing to kind of remind yourself of. Okay. Now, finding the critical values. That means we need the derivative. 200 minus 4x to be 0. You could probably do this in your head. Add 4x, divide by 4. X is 50. Now, you go back. I would always go back at the end and just say, okay, well, what did it ask me? It asked me for the length and width. So we should also get what y is. Using our equation here, 200 minus 2 times 50. So y is 100. So these are our dimensions. Okay, so the hardest part is always that setup, you know, getting it down to one variable. After that, the calculus part is actually pretty easy. Now, one last thing that I really should do to finish this problem off is do just a quick little sign analysis of my derivative with that critical point. And, you know, if I plug in a number less than 50, I get a positive. If I plug in a number bigger than 50, I get a negative. And I do that just to verify that I have found a maximum, because the derivative changes from positive to negative. Since there was only one critical point, I feel pretty confident I found the maximum, but it's good to check. Okay, I want to do one more here. We're going to calculate the smallest possible product of two numbers if one number is exactly 9 more than the other. Well, this is always kind of a fun problem, because people look at it and they say, well, geez, why don't I just pick, 0 and 9? Because their product is 0. Okay, but what about negative 1 and 8? Okay, that has a negative. The product is negative 8, so I can't include negatives. But if I get two negative, like let's say negative 10 and negative 1, negative 10 times negative 1 is positive 10. So we are limited here. There has to be a spot, a negative product that is the bottom. Okay, not really a great way to draw this picture and label it, but in a lot of problems there is. So don't lose that, but not a great way to do this one. Okay, I want to, in this case, minimize. Okay, process is the same, but I want to minimize my product. So I have two numbers. I'm just going to say the product is one number multiplied by the other. Okay. Now I'm going to use the information to relate them to one another. Why don't I just say that y is equal to x plus 9. There are a lot of different ways you could say this. I have set this up that x is the smaller number, and when I add 9 I'll get y. I certainly could have had x minus 9 and had x be the larger number, just remembering what I'm solving for at the end, but it really wouldn't have mattered. Okay, so now product was x multiplied by y. Now it's x multiplied by x plus 9. That's x squared plus 9x. The domain here really is all real numbers. I didn't say they had to be positive. I didn't say they had to be negative. So it's all reals. So the critical points, dp dx, is 2x plus 9. So I set this equal to 0. Subtract 9, divide by 2. X is negative 9/2, or negative 4.5. Y then is x plus 9, so it's positive 9/2. And their product, the product of the two, would be negative 81/4. Now, one thing I should by rights do here is, with my derivative, I should do a little sign analysis to just verify that it is in fact the minimum. So if I plug in a number less than negative 9/2, I get a negative. If I plug in a number bigger than negative 9/2, I get a positive. So you can see that it is in fact a minimum.